Every time a machine learning model improves, a loss curve is ticking downward. The system is systematically reducing its own uncertainty to find an answer. Beneath the complex architecture of every modern neural network and decision tree, there is a single foundational rule governing how they learn. This process traces back to 1948, when Claude Shannon published the mathematical framework of information theory. Shannon's entropy provides a definitive mathematical measurement of average uncertainty within any probability distribution. This formula quantifies ignorance in bits. A fair coin with a 50-50 split has exactly 1 bit of entropy, whereas a completely deterministic outcome, where the model is certain, has 0. Here lies a structural paradox. While basic supervised learning ruthlessly drives this entropy to 0, advanced AI systems must actively fight against absolute certainty to function. Controlling machine learning requires treating entropy as a physical lever, balancing the tension between rigid order and necessary chaos. The standard mechanism for training a classifier is the minimization of cross-entropy loss. This calculates the gap between true distribution, P, and predicted distribution, Q. For a single known example, it simplifies to negative log likelihood. This minimization is Kullback-Leibler divergence, the cross-entropy minus the true distribution's entropy, H of P. Because the training data is static, H of P remains a fixed constant. Lowering the cross-entropy loss is mathematically equivalent to lowering the KL divergence. This training process aggressively squeezes out the surprise between reality and the model's prediction. A diffuse cloud of widespread probability mass is aggressively compressed down into a single, razor-sharp, confident prediction. Gradient descent acts as the collector of this entropy tax, measuring and eliminating uncertainty in exact bits. Standard supervised learning operates as a mathematical war against disorder, forcing entropy to absolute 0 to ensure a confident prediction. Entropy was powering machine learning algorithms long before the rise of deep neural networks. Algorithms like ID3 and C4.5 navigate data by evaluating which specific feature split will most reduce uncertainty. This is information gain. It measures the deliberate drop in entropy that occurs as a parent node splits into its children. A perfectly pure, deterministic leaf node has an entropy of 0 bits. An evenly split uncertain node reaches exactly 1 bit. The decision tree greedily hunts for boundaries that extract the maximum amount of order from chaotic data. Modern random forests and gradient-boosted machines still rely on this same entropy-driven instinct to categorize data. Whether using gradient descent or recursive splits, the first era of machine learning was defined by the relentless pursuit of 0 entropy. But what happens when an advanced model successfully achieves the absolute certainty it was programmed to desire? In reinforcement learning, this triggers policy collapse. The agent becomes trapped by repeating a single suboptimal action. In generative AI, it leads to mode collapse. The model's latent space shrinks into a brittle singularity, preventing the creation of diverse outputs. Without uncertainty, the agent abruptly freezes. It repeatedly strikes a dead-end wall because its optimized math leaves no room to attempt a new path. This limitation connects back to Shannon's early experiments with mechanical routing and automated problem-solving. A simple classifier succeeds by achieving absolute certainty. For a generative model or an RL agent, that same certainty is a fatal flaw. System designers realized they could no longer treat entropy as an error to be eradicated. They had to weaponize it as a regularizer. In reinforcement learning, policy gradient methods actively append an entropy bonus term to their objective function. The hyperparameter alpha forces the agent's action distribution to spread out, rather than narrowing down into a single definitive spike. This injection of entropy provides a mathematical reward for curiosity, preventing the agent from converging prematurely on a single path. Entropy maximization is also a cornerstone of variational autoencoders, which utilize the evidence lower bound, or EBO. Expanding the KL divergence term within the EBO reveals an explicit mandate to maximize entropy. Maximizing the EBO simultaneously requires minimizing cross-entropy with the prior, while maximizing the entropy of the distribution Q. Injecting entropy forces the latent representation to spread out evenly across the space, preventing the model from collapsing into a singular, overconfident point. The data expands outward. The neural network builds a flexible map of possibilities, instead of a brittle over-optimization. This mathematical chaos is a deliberate creative spark, ensuring the model retains the flexibility required for complex learning. Modern AI performance relies on orchestrating a precise tension between rigid exploitation and chaotic exploration. Entropy provides the universal mathematical language for uncertainty across the entire spectrum of machine learning. Whether an engineer is reducing leaf impurity or increasing agent exploration, they are manipulating the exact same information theoretic quantity. Shannon's theoretical work provided the mathematical foundation for the hardware and software we use to build AI today. When a loss curve moves downward, the model isn't just fitting parameters, it is actively manipulating the amount of disorder in the system. Designing robust systems requires knowing when to squeeze uncertainty out of the data to find the truth. It also requires knowing when to sprinkle entropy back into the objective to keep the model adaptable. To build a system that can continuously learn, the designer must allow for a specific, controlled amount of chaos within the math. Entropy provides the mathematical pressure that allows artificial intelligence to evolve, adapt, and learn.